There's a little further kind of information about polynomials. So you should have already watched the video on the connection between factors and roots and how they give you x-intercepts. And you probably have already watched the video on finding x-intercepts or factoring higher degree polynomials, and again the connection with x-intercepts. And so just at least a couple little additions of concepts that weren't covered in those, but they're important. So one thing is, notice in this case there's a squared on this factor, which in a sense that means you could write this as 3x times x minus 2 times x plus 4 times x plus 4 times x minus 5. That's another way to write that, obviously. But the important thing to notice here is that it doesn't produce two different roots. So in other words, the root, if we were to write out the roots or the zeros, I keep using those words interchangeably because they are. The roots of this polynomial would be 0 because of that one, 2 because of that factor, and -4 because of that or that. I don't write -4 twice because there's not two different roots, they're the same root. And then 5 because of that factor. Now obviously there is something unique going on here. So what I normally do is put a little asterisk here, and we talk about that. That means that there is something special about that -4 root. And in order to talk about it, we need to bring up a new vocabulary word, multiplicity. So these roots, the first one, 0 has a multiplicity of 1, the 2 has a multiplicity of 1, but -4 has a multiplicity of 2. And then of course 5 is a multiplicity of 1. So multiplicity just talks about how many different factors produce that same root. So now, it doesn't mean there's an extra x-intercept somewhere because you don't have two different -4s on the x-axis. These are all the x-intercepts. So if I was to try to graph this, we would have a x-intercept of 0, 2, -4, and 3, 4, 5. Those are all my x-intercepts. So there's nothing different there. Now, if we go back and think about what we've done before, there's 1, 2, 3, 4, 5 different factors with an x in them. So that means that this would be a 5th degree polynomial. And it looks like the leading coefficient would be positive because all my x's are positive. So that would mean that it's a 5th degree, so it looks something like that, right? Where we have the end behavior on the right would be positive infinity, end behavior on the left would be negative infinity. So now, if we were just to draw that and cross at all the right places, it would look something like, whoa, we got a problem here. It didn't end up going up in the right place. So we know that there's something missing here. So let's erase that. So that's where this multiplicity comes in. So at -4, there's something different happening there. And one way to think of it, because this is a multiplicity of 2, that the intercept looks similar to a quadratic, which we know quadratics look like this or like this, right? So the idea is if you have a multiplicity of 2 is the graph actually, in a sense, bounces off of the x-axis instead of going right through it. So these all have a multiplicity of 1, which means they behave kind of like a linear equation. That would be a first degree polynomial at the x-intercept. This has a multiplicity of 2, so it behaves kind of like a parabola at the x-intercept. So that means I would start below like we thought, and I would come up, and -4 is where the multiplicity is, so it would come up and bounce off, and then it would cross like normal, and cross like normal. And so now you can see that it ends up, the end behavior ends up the way we expected, and this multiplicity of the multiplicity of 2 helps take care of that situation. Okay, So now this, again, this ability to draw kind of from scratch, again, as I've said many times, I'm not guaranteeing that all these points are right. I don't even expect them to be in the right place, other than I know the x-intercepts are right and the end behavior is correct. And I do know that this doesn't cross here, but it does cross at these other places. So now if I was to ask you a question like, where is this graph, where is this function positive and where is it negative? So because I can draw this quick sketch, I can very quickly obtain that information, because I'm looking at the graph and I know the crossings are right, and so therefore I know with confidence that this that f of x is greater than 0, aka that means also known as positive, right? If it's greater than 0, positive, that means it's positive. So where is it positive? Well, it's positive between 0 and 2, and then it's also positive from 5 on to infinity. Right? So we're just making a list using interval notation of where the graph is producing positive y values. Likewise, f of x is negative, aka, which means also known as, f of x is less than 0, also known as negative. So then we just list all the places where it's negative. So that would be from negative infinity to negative 4. Notice I'm putting a soft bracket there because it's actually equal to 0 at negative 4, so that would be negative 4 or positive. That would be negative or positive, a union, and then, but also again from negative 4 to 0, and then another union, and then from 2 to 5. So now all the x values are accounted for, except for the x-intercepts, and they should not be included in any of the intervals, because the y value is 0 at all those locations. So this is again determining whether the graph is positive and negative, which is really another way of saying is when is it above the x-axis and when is it below the x-axis.